Hey, would you like to see better at night? Well, what if roads glowed? If this were possible, it would be an incredible safety upgrade, right? No more traffic lights or street lamps needed. You could even find your way through a maze without having to rely on your sense of direction. But how exactly do you make a road glow? By shining light into its material. That's how. And since the glow would be coming from the road itself, it wouldn't matter if there were clouds or fog in the way. This is the basic principle behind photoluminescent road paint, which can be applied to traffic lines, road signs, and more. And while it doesn't quite reach the level of glowing as brightly as a big city street, this paint does glow enough to help drivers see where they need to stay in their lane or where they should stop. So how does this magical glowing paint actually work? Well, let's start with a look at regular fluorescent paint, which has been around since the 1960s. Like most paints, it comes in two parts: a liquid pigment suspended in a solvent and a binder which holds the color to whatever surface it is applied to. Once the paint is dry, the binder forms a film with tiny particles of the pigment embedded in it. These particles are specially designed glass crystals called phosphors. They're called phosphors because when exposed to light, they exhibit a phenomenon called phosphorescence. When the phosphors absorb energy from light, usually in the ultraviolet range of the spectrum, their electrons jump up to an excited state. Normally, these electrons would quickly drop back down to their original state, releasing energy as light and returning the phosphor to its original state. But some phosphors have an extra special property. After absorbing light, they remain in that excited state for much longer than other materials. That's because they're in an intermediate state between their normal state and their excited state. It's kind of like being stuck in an airport terminal between your departure gate and your arrival gate. You're not moving, but you're also not exactly standing still. And just like how you don't want to be stuck in an airport forever, the electrons don't want to stay in this intermediate state forever either. But unlike you in an airport, electrons can only leave this intermediate state by releasing energy in the form of light. However, the type of light they emit depends on the material the phosphors are made out of. Different phosphors release different colors of light when they finally drop back down to their normal state. Some phosphors will release red light, others blue, green, or yellow, and so on. So, depending on what you mix in, your fluorescent paint will glow a different color once it's been activated by UV light. Too much of one kind and the final color won't be bright enough, too little and it'll take too long to glow. These variables, plus the fact that each phosphor needs to be mixed with a special resin to keep it stable and prevent it from degrading over time, makes mixing fluorescent paint a tricky business. There's no simple one-size-fits-all solution. Each batch has to be custom made, but this careful mixing pays off. The paint is so efficient at emitting light that even after being diluted by up to a factor of 1,000, it still glows brighter than regular neon paint. And as you may have noticed, regular neon paint isn't all that great at staying fresh. Over time, it tends to degrade and become less vibrant. But photoluminescent paint stays strong through degradation. That's why this stuff is used to make those safety triangles you put in the back window of a car. Unlike regular paint, it can survive years of exposure to the sun without losing its glow. Now, if you want to use fluorescent paint to mark lanes or crosswalks, you have to make sure people can see it during the day as well. And this presents another challenge because the paint glows so brightly at night, it ends up looking dark during the day. People see the dark patch and assume it's just a shadow or part of the road, and they might not notice it until it's too late to avoid a collision. This is the reason many road markings during the day look black instead of white. The black color doesn't reflect as much light as white and therefore appears darker during the day, making it easier to see. One way around this is to apply a reflective material over the fluorescent paint. This reflective material consists of glass beads or flakes suspended in a clear solvent. When applied to the road, they settle in among the tiny raised bumps that give the road its texture. Since the glass beads are much more reflective than anything else on the road, they stand out to drivers even during the day. But this system has its own problems. Not only is the reflective material expensive, but the glass beads tend to wash away when the road gets wet. So engineers have developed a simpler solution, adding a bit of titanium dioxide to the fluorescent paint. Titanium dioxide reflects strongly in the visible spectrum, so it helps the road markings pop during the day, making them safer. This combination of fluorescent paint and titanium dioxide is a major improvement over regular lane markings, especially in bad weather. In experiments done in Germany, they found that drivers had a much easier time seeing lane markings during foggy conditions. Plus, because of its reflective properties, the paint can be seen even better by oncoming headlights, reducing the chance of a nighttime collision. Another advantage is that the paint can be customized to glow a different color depending on what part of the road it is used for. A hospital, for example, might use green paint to mark a path for ambulances or blue paint to help patients undergoing laser eye surgery find their way to the elevator. Artists have also started using photoluminescent paint to turn ordinary roads into interactive art installations. With funding from the European Union, artists turned part of a Spanish highway into a gigantic piano keyboard and part of a Danish road into a giant clock face. Drivers can interact with these artworks by driving over them and leaving glowing tire marks. Photoluminescent paint is also being tested to mark offshore oil rigs and shipyards, allowing workers to easily find their way through the dark. And speaking of ships, the U.S. Navy has developed a photoluminescent coating they can apply to the bottom of ships to make them glow in the dark. This helps the ships blend in with the bioluminescent algae and plankton that often surround them, helping them hide from sonar. Now, we haven't even scratched the surface of all the ways this technology can be used. Photoluminescent concrete is being tested in Europe and Asia. It could replace street lamps since the concrete would glow thanks to exposure to daylight. Architects are experimenting with photoluminescent glass that can glow different colors when exposed to varying degrees of UV radiation. One architect who goes by the name of Solaris uses photoluminescent glass panels in many of his buildings. His designs use the panels to collect energy during the day and then release it as light at night, dramatically reducing the building's energy costs. One of his buildings in France uses this technique to project ever-shifting patterns of light onto the walls of nearby buildings. So it turns out the idea of glowing roads isn't that far-fetched. Thanks to advancements in nanotechnology, scientists are even able to precisely control how long different phosphors will stay in their excited state. This means it is now possible to mix together phosphors so that different parts of a painting glow different brightnesses or even pulse in sync with each other. And who knows, maybe someday soon roads will glow, and all because of a little bit of physics. Speaking of physics, we love physics, and we know you do too. That's why we were so excited to partner with companies whose mission is to help people learn science in the easiest and most engaging way possible.